We saw how we can define matrix vector multiplication. Here we're going to kind of consider that idea of matrix vector multiplication and look at an equation that includes some matrix vector multiplication, specifically an equation of the form AX equals B, where A is a matrix and X and B are appropriately sized vectors. So we'll start with an example. Let's say we have a 3 by 3 matrix A, 1, 2, -1, 3, 1, 4, 2, -1, 5, and a vector B in R3, -3, 17, 20. We might ask the question, can we find a vector X such that the matrix vector product A times X equals B? First of all, we would want to kind of figure out what space X would live in, what dimension it would be. In this case, it would have to be in R3. So if we could find such an X, then X might take on the form x1, x2, x3, and multiplying A times X, we would get, let's just kind of go through this. So there's A. If we wanted to multiply this by X, x1, x2, x3, then we define this in a previous video. This would be the vector where we would look at the linear combination of the columns of A, where the weights are the components of our vector x. So that means we would have the vector x1 times the first column of A, 1, 3, 2, plus x2 times 2, 1, -1, plus x3, oops, plus x3, ourselves a little space there, times the vector -1, 4, 5. And so, putting all that together, we would end up with AX looking like the vector x1 plus 2x2 minus x3 as our first component, and then 3x1, x2, plus x2, I should say, plus 4x3 as our second component, and then 2x1 minus x2 plus 5x3 as our third component. So there's our AX, right? This is our AX, and we want to know, does that equal B? -3, 17, 20. So we've got this AX equals B. And so if this were to have a solution, then it would mean that the components of each of these vectors would be equal to each other. So that basically means that we'd have x1 plus 2x2 minus x3 equals -3, and then 3x1 plus x2 plus 4x3 equals 17, and then 2x1 minus x2 plus 5x3 equals 20. And hopefully this is starting to feel familiar. What we've ended up here with is a system of equations. So we know that we can kind of construct the augmented matrix. So maybe I will give myself a little bit of space over here and construct the augmented matrix that would be the matrix that we would have to row reduce in order to solve this particular system. So this system will have a solution if we can row reduce this and get a solution, as we've seen in earlier sections. So we'll have this augmented matrix 3, 1, 4, 17, and then 2, -1, 5, 20. And so this equation, AX equals B, will have a solution, X, precisely when this augmented matrix here, can be row reduced and show us a solution, because then, we would have a solution to this system. And what you might see, in terms of this augmented matrix is we've basically just stuck our matrix, our original matrix A, right, as our kind of coefficient matrix, and then the right-hand side is just this vector B. So we've kind of landed, we took a big detour, we went around kind of carefully using our definitions, but we landed on, sort of a matrix here that has the form A as the coefficient matrix, and then the vector B as the right-hand side, that we can then row reduce. Now, I'm not going to take the time right now to like sort of go through the row reduction and solving this. You're welcome to either try that on your own or use some technology, but the point here was just sort of to set up this relationship that we'll be exploring a little bit more as we move forward in this section. So there's sort of three different interpretations that we want to kind of consider here. So suppose we have, just for an example to begin with, a vector A consisting of the columns v1, v2, v3, and then the vector x consisting of the components x1, x2, x3. So A times x, this matrix vector multiplication, would look like this: x1, v1 plus x2, v2 plus x3, v3. And as we saw in the previous example, the matrix vector multiplication can be interpreted as solving a matrix equation. So sort of considering that like A times X equals B. So AX equals B. That's that matrix equation interpretation. Forming a linear combination. So that's sort of like the general setup: x1, v1, x2, v2, x3, v3, and then also solving a linear system. So, that was that linear system with augmented matrix of this form. And this brings us to proposition 224, which basically does this more generally. Says that if A is the matrix whose columns are the vectors v1 through vn, X is the vector in Rn whose components are x1 through xn, then the following statements are equivalent. The first is that the vector x satisfies the equation Ax equals b. The second is that the vector b is a linear combination of the columns of A with weights given by the components of x. In other words, b equals x1 v1 plus x2 v2 plus dot 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 xn vn. And then finally, the components of x form a solution to the linear system corresponding to the augmented matrix v1, v2 through vn as the coefficients, and then b as the right-hand side. So this this kind of augmented matrix that we've been looking at, where we've got A as the coefficient matrix. And so the kind of key here is that we're connecting this equation, this Ax equals b, to the concept of linear combination, to the concept of a linear system. So we want to sort of keep those three interpretations in mind and understand sort of that they're equivalent and how they're equivalent. Let's take a look at one more example here. So if we have A and B, if we want to solve Ax equals b, we don't necessarily have to go through all the steps that we went through before. We can just jump now to knowing that this will have a solution precisely when the sort of system that corresponds to the augmented matrix that I'm going to draw here, where we've got A as the coefficients and B as the right-hand side, has a solution. So 2, 4, -2, and then 6, 1, 1, 1, 2. Okay, and maybe this one I will row reduce just to have a little more practice with that. So we might take R2 minus 2R1 and R3 minus R1. 1, 2, -1, 3, and then 2 minus 2 is 0, 4 minus 2 times 2, so 4 minus 4, that's another 0. -2 minus 2 times -1, -2 plus 2, that's another 0. And then 6 minus 6, so that's another 0. So we've got a row of zeros there. And then 1 minus 1 is 0, 1 minus 2 is -1, 1 plus 1 is 2, and 2 minus 3 is -1. Let's do an interchange here to bring that row of zeros to the bottom to -1, 3, and then 0, -1, 2, -1, 0, 0, 0, 0. Let's scale this second row by a -1 to put just +1 in that position. We have a 0, 1, -2, 1, 0, 0, 0, 0. And then I think one more step gets us to reduce our echelon form. So we'll have row 1 minus 2, row 2, 1, 2 minus 2 is 0, -1 plus 4 is a 3, 3 minus 2 is a 1, and then 0, 1, 1, 0, 0, 0, 0. So we do have a consistent system here, which means that we've got solutions, and we also have a column without a pivot, namely column 3 here. And so that tells us that we have infinitely many solutions. Let's actually go ahead and write out sort of a way of describing those solutions. So we might have, the components of this vector x, we might call them x1, x2, x3. So x3 would be our free variable. We'd have that x1 would equal 1 minus 3x3, just sort of taking that first row and solving for x1. And then the second one, we'd have x2 would equal 1 plus 2x3. And then I like to write for my free variables just x3 is x3. It can be anything we want, so we can write that. And so one way we're going to learn to write this is in what it's called the parametric form. So the vector x, the solutions, are all going to have the form of the vector 1, 1, 0, so the kind of constant terms, plus x3 times -3, 2, 1. Okay, and so basically what we can see here is that all of our solutions are going to have this form where we've got this vector 1, 1, 0, and we are adding constant multiples of the vector -3, 2, 1. If we're thinking kind of geometrically about what that might look like, when you add a vector to, maybe we'll call this sort of vector v, let's say, plus x3, which is a constant, any scalar we want, it's a free variable, and then maybe this is w. So we've got our solutions are of the form v plus some scalar times w. That is going to ultimately be a line in 3 dimensions. Sort of all the points or all the vectors, if we kind of connect their endpoints, let's say, then we'd end up with a line in 3 dimensions. So something we're going to be doing as we move forward here is kind of, trying to describe these solution spaces, specifically when we've got systems that have infinitely many solutions.